To start with, a little reminder about graphs of inequalities. So if I'm going to write an inequality for this graph, let's figure out the equation of my boundary line. So if I do y equals mx plus b, my y-intercept is 5 and my slope is 2. And then since this is an inequality, it's not just all the points on the line, it's the points that are kind of below and to the right of it. So let's say maybe it's less than 2x plus 5. Check that and see if it works. If it doesn't work, it would need to be greater than instead. So test a point that's not on my boundary line. I'm going to do 0, 0. If I plug that into my potential inequality, I get 0 is less than 5, which is a true statement. So the inequality that I wrote works. Since it's not a solid line, it's a dashed line, the points on the line are not included, which is why I did less than and not less than or equal to. Okay, so hopefully that jogs your memory a little bit. To start with, we're just going to take some points and see if they are solutions to this system of inequalities. So let's see if 0, 0 works in both of those inequalities. If it does, it's a solution. Well, right away, if I plug 0 in for x and y, it doesn't work in the first inequality, so I don't even need to try it in the second one. It's not a solution. If I try 2, 7 in my first inequality, I get 7's greater than 5, which is a true statement. It's going to have to work in my second one as well to be a solution. If I plug it into my second one, I get 2 plus 2 times 7 less than 18. That's also true. So if a point works in both of my inequalities, it is a solution to my system. If I try 4, 6, well, 6 isn't greater than 9, so nope, not a solution there either. All right, so let's graph some systems of inequalities. You just want to graph each inequality individually, and then locate the region where they overlap, because those points that work in both are your solution to your system of inequalities. So I'm going to graph my boundary lines first, which on my first one is y equals 3x plus 2, just like I'd graph that line normally, y-intercept of 2, slope of positive 3, and then it is an or equal to, so it should be a solid line. My solution set includes the points on the line. Now I need to figure out where to shade. So let me test a point that's not on my line. I'm going to do 0, 0 because it's easy to plug in. So if I plug that in, I have 0 is less than or equal to 3 times 0 plus 2. 0 is less than or equal to 2, which means 0, 0 is in the region that is a solution. So if I locate 0, 0 on my graph right there, the points on that side of my coordinate plane, on that right-hand side of my line, are solutions to that first inequality. Okay, repeat for number 2. Let's graph my boundary line. Negative y equals 2x, which means if I solve that for y, I get y equals negative 2x, y-intercept of 0, slope of negative 2, and it is a less than, so it's not going to include the points on the line, so when I put that in here, I'm going to use a dashed line for that boundary. All right, now I need to plug in a point and test it. I need a point that's not on my line. It's got to be on one side or the other. So let's not do 0, 0. Let's do 1, 0. If I plug that into my original inequality, by the way, if you solved that original inequality for y and are using that to test, I hope you remember to flip the direction of your inequality symbol. I got 0 is less than 2, which is a true statement. So the point 1, 0 is in the region that is my solution. And then if I shade my overlap and make it nice and dark so I can tell, my solution is all the points that work in both inequalities. Let's look at a couple more. So this one, if you think about it, that first inequality is bounded by vertical lines because it says x is greater than 1 and x is less than 4. So if you think about the points that will work, all the points with x values in between 1 and 4, and including 1 and 4, are solutions, so it's just those vertical lines and all the points in the middle of them. If you look at y is less than or equal to 2, well, that's a horizontal line for my boundary line. And if I'm thinking about all the points that have y values less than 2, that's all the points below my boundary line. I could also pick a point still, plug it in and test it. I wouldn't be plugging in at the x value anywhere, but I could plug in like 0, 0, and have the y value 0 be less than or equal to 2, and it would still show you what points work. So my overlap is the points that are below my horizontal line and in between those two vertical lines. Let's do a nonlinear one. So if you think about the first one, my boundary is the parabola y equals 1/2 x squared. So that's not translated left, right, up, or down, so its vertex is going to be at 0, 0. Let me get some additional points by picking some x values and plugging them in. So if I plug in 1, I get 1/2. If I plug in 2, I get 2. Let's reflect those over my axis of symmetry, and it is an or equal to, so I'll use a solid line. Again, I need to test a point and plug it in. So let's do 0, 1. If I plug 0, 1 in, you get a statement that is true, which means the region where the point 0, 1 is part of your solution for that inequality. So that's inside my parabola there. All of those points work. If I look at my other inequality, that's the boundary line y equals 2x plus 2. Almost plotted the wrong y-intercept there. It is a dashed line. Let's branch out. I'm going to test the point -2, 0 here. So if I plug -2 in for x and 0 in for y, I'm going to get 0 is less than -2, which is not true, which means the region of my coordinate plane where -2, 0 is not the points that are solutions. So I need to shade on the other half of my coordinate plane instead. My overlap is my region that is below my purple line and still above and inside my parabola, so my solution points are in there.